This is part 8 of the series Quadrilaterals, and in this part we're going to continue with our discussion on trapezoids, and we're looking at the next property of trapezoids given by the isosceles trapezoid base angles converse theorem. And it says, if a trapezoid has one pair of congruent base angles, then it is an isosceles trapezoid. This proof is going to look very similar to the proof that we did previously for the isosceles trapezoid base angles theorem, but it's going to be a little bit different. So let's get into it and see what's different. Now the plan for this proof is to somehow show that AB is congruent to CD. And the way I'm going to try and do that is I'm going to draw in an auxiliary segment, CE, that's parallel to AB. That will make AB congruent to CE because it's a parallelogram. Then I'm going to use the idea of these congruent opposite angles and supplementary consecutive angles in the parallelogram to show that this angle is congruent to this, thereby making this side congruent to this side, and because this side is congruent to this by the parallelogram opposite sides theorem, then this is going to be congruent to that by the transitive property of congruent segments. So that's a really rough sketch overview of the plan for the proof. So let's get started and go ahead and do our first step, which was draw in CE parallel to AB. Then we write draw CE parallel to AB. That's the parallel postulate. And we now know that ABCD is a parallelogram by the definition of a parallelogram, quadrilateral with two pairs of opposite parallel sides. We're trying to generate a linkage between this side and this side, and we're going to do that through these angles. So to start that process, we're going to show that these two angles are congruent because of the parallelogram opposite sides theorem. And then we're going to show that since these are a linear pair, and these are supplementary, that this angle is going to be congruent to this, and therefore this is congruent to that. We state angle B is congruent to angle AEC by the parallelogram opposite angles theorem. Now we want to state that this angle and this angle are linear pairs and that they're supplementary. So let's do that. We state angle AEC and angle CED are linear pairs. So AEC, CED are a linear pair. That's the definition of a linear pair. And AEC is supplementary to LED. These two angles are supplementary. That's the linear pair postulate. We also know that angle A is supplementary to B, and we can state that because of the consecutive interior angles theorem. So we're going to state A is supplementary to B. So we've stated that angle A is supplementary to angle B. Since we've stated that this is supplementary to this, and this angle is supplementary to this, and these two angles are congruent, then we know that this angle must be congruent to this by the congruent supplements theorem. We were given that angle A is congruent to angle D, and we just showed that angle A is congruent to angle CED. Therefore, angle CED is congruent to angle D by the transitive property of angle congruence. Now that these two angles are congruent, we know that CE has to be congruent to CD because of the converse of the base angles theorem. So the end is just about here. We know that these two are congruent, and we know that this is congruent to this by the parallelogram opposite sides theorem. So then we're going to know that AB is congruent to CD by the transitive property of segment congruence. So we've stated AB is congruent to CD, AB to CE, and AB is congruent to CD by the transitive property. So AB congruent to CD. Now finally, we know that ABCD has to be an isosceles trapezoid. the definition of an isosceles trapezoid is a trapezoid with congruent legs. So these legs are now congruent, so the trapezoid is isosceles. And that would be our final statement. And to close, trapezoid ABCD is isosceles by the definition of isosceles trapezoid. Again, another fairly involved proof, but go through it again and try to see if you can follow the steps. Perhaps even see if you can do it yourself, maybe come up with an optimization of your own, and it should help you along the way. And now we'll move on to the next section. The next property is given by the isosceles trapezoid diagonals theorem. A trapezoid is isosceles if and only if the diagonals are congruent. Again, this is a biconditional, and you can say that if a trapezoid is isosceles, then the diagonals are congruent, or if the diagonals of a trapezoid are congruent, then the trapezoid is isosceles. So we're going to go ahead and pick the first one, and that's the condition we're going to use for our proof. So let's go ahead and look at that. Here we're given trapezoid ABCD is isosceles, and we need to prove that AC is congruent to BD. The plan for this proof is fairly basic if you can visualize triangles ABD and triangles ACD being separated. If you have trouble, go ahead and separate them, because that will help you a great deal. So I'm just going to write up here, I'm going to try and sketch, and it doesn't have to be perfect. Just sketch your two triangles and relabel them. So this is A, B, and D. This is A, D, and C. And so I'm going to show that these two triangles are congruent, and therefore those two sides are congruent, which are the diagonals, by CPCTC. Now, let's go ahead and work this. The first thing we want to do is to show that angle A, or angle BAD, so that's this angle, is congruent to CDA, which is this angle. And we know that because since this is an isosceles trapezoid, the base angles are congruent. We also know that AB is congruent to CD, and that's given in the definition of an isosceles trapezoid, that it's a trapezoid with congruent legs. So let's write that. We're making good progress. We have AB is congruent to CD, so here these two are congruent, and we have these two angles are congruent. Now, if we can just show that this is congruent to this, we can prove that these two triangles are congruent. And in fact, AD is shared with both of these triangles, so we can say that AD is congruent to AD by the reflexive property. So just to make our drawing complete, we show AD congruent to AD by the reflexive property of segment congruence. We now know that this triangle is congruent to this by side, angle, side. Side, angle, side. So let's make that statement. So here we have triangle BAD congruent to CDA by side, angle, side congruence. And now we can show that this is congruent to this. BD is congruent to AC by CPCTC. Corresponding parts of congruent triangles are congruent. This is a much simpler proof, and the key was in separating these two triangles. It's not necessary if you have really good spatial reasoning skills, but it never hurts to actually draw your own picture so that you can internalize the relationships in these two triangles and in the shape in general. So now let's move on to the next section. Here we have a fairly basic problem. They give us an isosceles trapezoid. We know it's isosceles because the legs are congruent and we have one pair of parallel sides. It's asking us to fill in the measures of the missing angles. This should be fairly straightforward because we know that in an isosceles trapezoid the base angles are congruent. So this angle is 85 degrees. And we know that the consecutive angles are supplementary. So this angle has to be 95. And these base angles are congruent, so that angle has to be 95 as well. So that was just a quick basic example of the properties of isosceles trapezoids. Let's go ahead and move on to the next section. The last idea we're going to look at in terms of trapezoids is going to be the trapezoid midsegment. Definition of a midsegment is a segment that connects the midpoints of the legs. So that means that AE is congruent to ED and BF is congruent to FC. The trapezoid midsegment theorem says that the midsegment of a trapezoid is parallel to the bases and its length is 1/2 the sum of the lengths of the bases. So EF here is 1/2 AB plus DC. Let's use this in an example and see what's going on here. In this example we have a trapezoid, and this is a midsegment because this is congruent to this and this to this, therefore N and M are midpoints of their respective legs. So since this is a midsegment, we know that this length is 1/2 the sum of these. So let's put that down. MN is 1/2 12 plus 28, which is 1/2 of 40, which is 20. Pretty basic example. Let's move on and see what else we have. In this example, we want to find the length of the midsegment of this trapezoid. So it's the length of something right about there. Now we have a couple of options to do this. One, we could find the coordinates of the midpoints of the legs. So find the midpoint of that leg and the midpoint of this leg and use those coordinates in the distance formula to find the length of that midsegment. Or we can use the midsegment formula and just go straight to the distance formula for this side and this side, add those two values up and divide it by 2. I'm just going to jump in and find the length of AB and DC and see where that leads us. Let's take the coordinates of AB, 0, 6, and 2, 2. This is going to be AB. And subtract. 0 minus 2 is -2. 6 minus 2 is 4. Square, add square roots. 4 plus 16. So that's the square root of 20. Then I'm going to do CD. CD is 8 and 10, 12 and 2. 8 minus 12 is -4. 10 minus 2, 8. Square, add square root. 16, 64, square root, and that's the square root of 80. So we can simplify these. That's 2 and 10, 2 and 5, so that's 2 square roots of 5. And this is 2 and 40, 2 and 20, 2 and 10, 2 and 5. So we have 2 pairs. So we have 4 square roots of 5. And so our midsegment, whatever that is going to be equal to 1/2 2 square roots of 5 plus 4 square roots of 5, which is 1/2 6 square roots of 5, which is going to be equal to 3 square roots of 5. In case this slipped by you, this is just a prime factor tree. I just took all the prime factors of 20, 2, 2, and 5, and the prime factors of 80, 2, 2, 2, 2, and 5. And every pair of 2's comes out of the radical as one of those 2's. So we had 1, 2, another 2, so that's 2 times 2, which is 4 coming out. All right, let's move on to the next section.